Greetings, math friends. We are going to look at some real analysis, and I am using as my guide today this book, Intermediate Mathematical Analysis by Anthony E. Labarre Jr. It was originally published in '68 and was republished by Dover in 2008. It's now out of print even with Dover. I want to look at the problem of finding the accumulation points of the prime numbers. And we're going to want to use the definition of an accumulation point for that. So according to Labarre, we have a definition that some set of numbers, A, which is going to be a subset of the real numbers, is going to have some point that's not necessarily in A that is going to be this accumulation point. It can also be called a limit point, but that's kind of confusing because we need to emphasize that an accumulation point is not a limit for a sequence. Okay, but unfortunately, this is where some of the nomenclature in mathematics is confusing. Some people call this a limit point, and he notes that in here that they call it a limit point, but it's also called an accumulation point. And that's really the vocabulary we want to use, is that this is an accumulation point. So we have this point, and we want to look at a neighborhood around that point. So we need to choose some epsilon greater than 0. So some small number larger than 0 that's going to be around this point. And this is what can be called a deleted neighborhood. It doesn't matter if that point is even there or not. We're just looking around that area. All right. So RA is going to be the set of prime numbers. This, of course, is a set of the real numbers. It's a subset of the natural numbers. So we're looking at numbers that are divisible by only 1 in itself, but by definition excluding 1. So our first number in our set A is going to be 2, and then it goes up from there, and it is established by another theorem that this set is infinitely big. There is no upper bound. So, being that we need some epsilon greater than 0, we are going to choose 1/2. All right? You can choose any small number. I'm using 1/2 as my example here. All right? So now I need to choose some x that's a real number, and again, this point does not have to be a member of A. It can be any real number. And then we're going to have a variety of things that we need to consider with this. So the first thing that I want to consider is I want to choose my x so that it is definitely not a prime number. All right. And that number could be somewhere out here beyond the smallest prime number. It could be a number in between prime numbers. Okay. Any number over to the right here, that is really a number between prime numbers because, again, there's no upper bound here. So there is some number after 17 that is prime. So any number that we choose over here is not a prime number, but it is a real number. All right. So if we choose some number, what happens? Well, we have to look at the neighborhood around that point. So, for instance, if we choose that x being not a prime number is, let's say, 2.5. All right, it falls between 2 and 3 here. Okay, so this is a real number that is not a prime number. And the neighborhood around 2.5, so we're going to add 1/2 and subtract 1/2 because that's the epsilon that I've chosen here. If I add a half, that means I'm here at 3, and if I subtract a half, that means I'm here at 2. All right? So if this is an open interval, technically 2 and 3 are not a part of that. Okay? And that's what we typically look at as an open interval. So we don't count the endpoints when we add a half and subtract a half. So if it was a closed interval, it definitely includes 2 and 3. But if it's an open interval, it doesn't include either 2 or 3. So we have no points in this deleted neighborhood that is part of A. So this 2.5 is not an accumulation point. 2 and 3 are as close as you're going to get for prime numbers. Any other place is either a elementary distance of 1 apart or larger. So like between 3 and 5, there's an elementary measure here of 2. So this is essentially our smallest distance between points. If it doesn't work here, it's not going to work for any of the other prime numbers. If you would have chosen your x, say, out here somewhere, well, you may not even be this close to a prime number. All right? So that's not working for us. So option 2, let's suppose that x is the infimum of A. So in other words, the smallest value, the greatest lower bound. What's the largest number that I can choose that is smaller than any other value in here, or equal to the smallest value in my set? Well, 2 is going to work for that. All the other prime numbers are larger than 2. If we let 2 be the center, well, that's an even worse situation, because 2.5 didn't work, so 2's not going to work. If it's a deleted neighborhood, it doesn't contain 2. If you consider it a neighborhood including your center, well, then it contains 1 point from A. So you have to determine, do you care about a deleted neighborhood or not? Either way, 1 point is not good enough to be an accumulation point. All right. Third condition would be, well, perhaps if the infimum doesn't work, maybe the supremum would work. So what about an upper bound? Well, there is no upper bound of A, so you can't have a supremum, so that option is out of the question. So is there a fourth condition or more that we need to consider as we consider this? Well, you could attempt to choose any prime number arbitrarily from A. All right, so let's just choose any prime number that you wish to be the center. And again, you can consider this a deleted neighborhood or a neighborhood containing the center. All right, so let's just randomly choose 11. All right, what if this is x? Well, if I add a half to 11, this is 11 and a half. If I subtract a half from 11, I get 10 and a half. All right, so this is the neighborhood that I'm looking at here. If the neighborhood contains the center, then we've got 1 element in here. If it's a deleted neighborhood, meaning we don't have to consider the center, well, then there's no elements of A in here. And you can essentially do this. This is arbitrary right? You can choose any of the prime numbers that you would like. We've already considered 2 and it didn't work because that was the infimum of the set. All right. 2 and 3 were really close together. That's as close as you can get. And choosing the midpoint between those also didn't work for us. So I think these are about the 4 cases we really need to consider. We can at this point conclude, since 1, 2, 3, and 4 fail to contain elements or multiple elements of A, there are no accumulation points for the set A. All right, so I've done this as a 4-step process to allow me to slow down and think about what is going on in the search for accumulation points of a set. So I've tried to break out the different conditions that need to be considered when we are given a set A that is a proper subset of the real numbers, and then to determine in a case-by-case basis whether we can see the properties of the accumulation point according to the definition. In this particular case, we cannot find accumulation points of the prime numbers. I hope this has been an educational approach for you to see how we should consider the search for accumulation points. Again, I want to stress that an accumulation point is not actually the limit for a sequence. If we would look at where the sequence is going, this is going to be divergent since there's no upper bound. If we approach the other direction, though, we do have a lower bound here. There are different conditions that happen. We do need to also have that we start out with an infinite set. If we don't have an infinite set of points, then you're not going to find accumulation points for those sets at all. I hope you find some interesting mathematics that you can share with others in your part of the world. Cheerful calculations.